Example 16.6. In this example, we consider a person standing in a breezy room at 20 Celsius. We need to determine the total rate of heat transfer from this person if the exposed surface area and the average outer surface temperature of the person are 1.6 meters squared and 29 Celsius respectively. The convection heat transfer coefficient is equal to 6 watts per meter squared Kelvin. We're going to take this example to be a steady, and we're going to assume that the person is completely surrounded by the walls and the ceiling and the roof, and we're going to neglect conduction. Notice that this example is similar to the one done previously, example 15.5. However, in this case, we're going to have both convection and radiation taking place. The only mode of heat transfer that we are neglected is going to be conduction. So we're going to start with the definition of the heat transfer rate for convection. That is going to be equal to H, surface area, T of the surface, minus T infinity. On the other hand, for radiation, we have the rate of heat loss for radiation is equal to epsilon, sigma, surface area, Ts to the 4, and T infinity to the 4. So notice that in this case, we're going to assume that the T surrounding and T infinity are both equal to each other. Okay, so notice that for the convection, we have all the information provided. We have the value of the heat transfer coefficient, the surface area, and both of the temperatures. So we simply replace. So this is going to be 6 watts m squared Kelvin. The surface area was given to be 1.6 meters squared. The surface temperature, so is the skin temperature or the body temperature, was given to be 29 Celsius. And the outer temperature of the room is at 20 Celsius. So notice that what we have over here when we calculate, this is going to give us 86.4. Now let's look at the units. Meter square cancels with meter square, and Kelvin cancels with Celsius. Remember, once again, you could cancel the delta of Celsius with the delta of Kelvin since they are exactly the same. Therefore, the unit left is going to be watts. The second component is going to be radiation. So for radiation, the first thing that we need is the value of epsilon. Epsilon is obtained from table 16.6, and the value for the skin is equal to 0.95. Once again, this is from table 16.6 in the textbook. So now we're going to calculate the value of the heat rate of radiation. So we have simply, we use the value that we have for epsilon, 0.95. The Stefan-Boltzmann constant is equal to 567 times 10 to the negative 8 watts m squared Kelvin to the 4th. The surface area was given to be 1.6 meters squared. The temperatures that we have are 20, once again the same ones that we have over here, 29 and 20. However, they have to be in Kelvin. So we do 29 plus 273, and this is Kelvin, and then we have to do it to the 4th, minus, we have 20 plus 273, and this is Kelvin once again to the 4th. So the value that we obtain over here for the heat rate loss of radiation, it's going to give us 81.7 watts. And we double check the units once again. So this is meter square cancels with meter square. This is Kelvin to the 4th cancels with this Kelvin to the 4th. And that's what we get, watts. So now notice that we have the two values for, this is for convection and this is for radiation. Notice that the order of magnitude are very, very similar to each other. Now if we want to find out the total value of the rate of heat loss, is simply the addition of these two values, so it's 86.4 watts plus 81.7 watts, and it gives you about 168.1 watts. Okay, so notice that for this particular example, since the order of magnitude of both radiation and convection are about the same, you are not allowed to neglect either one of them.